In this video, we're going to take a look at one of the pwn challenges that are created for the Intigriti Leads Up Live CTF 2024. It's quite an easy challenge. It's about all I know how to make or solve when it comes to pwn these days. And you can see that I've already checked the file type on the screen. It's a 64-bit binary, it's not stripped, and we've also got the binary protections up here. So if you do some pwn challenges, you might look at these protections to try and get an idea what the challenge might involve. For example, there aren't any canaries on the stack, which means there's a good chance we'll be able to overflow the buffer. However, NX is enabled, so if we do that, we're not able to execute any shellcode that we inject onto the stack. And if there are any interesting functions or gadgets that we want to use in the binary, we're not going to have to worry about leaking those addresses because every time we load the binary, it's going to be the same base address. Okay, next let's just run the binary and see what it looks like. We get three options. We can explore the forest, let's do 1. We can battle the dragon, let's do 2, and we can quit, so that's 3. So nothing particularly interesting, we didn't have any further options. Maybe we could just try and put in a long input here, and yep, that's not working for us. Let me redo that, let's select. There's literally nothing else we can do. Alright, so we're going to want to go and decompile the binary and see what's actually happening. You could just open this up with GDB if you're happy looking at the assembly. I'm going to open up ghidra, and then we'll get a better output closer to the original C code that the binary was written in. I've got an alias set up to do this, which is why I'm using that ghidra auto script, and this will just skip a lot of the checks that we normally have to click OK or yes to. Okay, so we've got our disassembled code on the left, and then we've got our decompiled code on the right. This is basically the C code that was used to compile the program. It won't be exact, but if you just copy and paste this and give it to ChatGPT, you can probably get a version that will compile straight away. I like to rename things here, so I'm just going to rename this to menu option, and that's the number that we provide when we start. So if it's not a 2, it will battle the dragon. A very weird way that this compiles, but yeah, if it's not 2, it's going to battle the dragon. If it's a 1, it's going to explore the forest. If it's a 3, it's going to quit the game. But there's also a hidden menu option that we don't see when we just run the program, and that has a decimal value of 1337. So if we run the program again, and now do 1337, notice it takes us through to this cheat code function. So you can see here, cheat code, enter cheat code. And this function has a buffer, which is for our cheat code, and it's 16 bytes, but it's calling this dangerous gets function, which is dangerous because it's not checking that this buffer will fit whatever the user enters. So we could enter 200 characters here, and it's not going to see, does this buffer have enough space for 200 characters? Hence, we can overflow the buffer. I guess I didn't design this quite right. I wanted it to actually ask for the cheat code. It did originally. I think I fixed the looping menu option, and it's obviously broken this at the same time, but I think the exploit will still work. Let me just test this now. Let's do 1337. And then let me type, this is the cheat code. Alright, so yeah, it's a little bit buggy, but as long as the exploit works, which hopefully it does. Let's go back here. We've identified a potential buffer overflow, but what are we going to do with it? We know that we can't inject shellcode onto the stack and make it execute. Let's have a look at the functions down here and see if there are any other interesting ones. We have enter cheat code. We also have a cheat mode. And this cheat mode has a mention of the flag, so maybe we could have just done like a string search to try and find this to begin with. And let's see, it takes 2 parameters, param1, param2. It's going to make sure that those params equal these values, so I guess that's the cheat code. And if it does, it's going to activate cheat mode, which is going to open the flag and print it. I don't really need to rename these variables, I guess at this stage we can. Just assume that what we need to do is overflow the buffer and redirects the flow of execution to this function. But in order to get the flag, we're also going to need to make sure that these parameters are properly set up. And when it comes to 64-bit binaries, which this is, that means we need to prepare these parameters in the relevant registers. So we basically want to first pop this value into the RDI register, and then we want to pop this one into the RSI register, and then we call this function. And whenever it calls cheat mode, it will then go and look in those 2 registers for those parameters, which is why we need to prepare them beforehand. If it was a 32-bit binary, we'd just be able to pass in those parameters after the function call, but it's just a different format when it comes to 64-bit. So we could go and play around with this in GDB. I like to do that just to see how things look whenever we do overflow that buffer. And we want to try and work out what is the offset. So how many bytes do we need to write in order to overflow that buffer? Where was it? Main. Yeah, the enter cheat code one. So, well, we've got 16 bytes here. It's probably not going to be exactly 16. I think probably 24. But let's find out. Let's do gdb pwntools, and we pass in the binary name. We'll generate a cyclic pattern. I'm going to do 100, and I'm going to take a copy of this. Let's run it. Let us put in 1337, and then we need to put in that long code because I didn't design the program properly. And it crashes the program because it's trying to execute an invalid instruction, which is this. So basically, we can look and see what is in the RSP. So you've got this D and then 7 A's, and then I'm going to do cyclic-L to look that up. And it's found it at 24, yeah. So we've got 24 bytes that we need to overwrite before we'll have control of the instruction pointer. And we want to point the instruction pointer to the cheat mode function, which will print a flag. But first, we need to go and set up those parameters. And actually, maybe we won't do that first. Maybe we'll just do this just as a demonstration without it. Okay, I've just done exactly that. So I've just taken a pwntools script that I use for pwn challenges, and I just showed how to manually get that offset to the EIP, or for the RIP in this case, in GDB, but you can also do that through the pwntools script, which is exactly what this is doing. It's going to send 64 bytes of the same cyclic pattern. It's going to crash the process, and it's going to have a look at the stack and see what was in the stack pointer before the program crashed, and it'll find that it was that D and then 7 A's, and it'll know, okay, the offset is 24, and that's what we're going to use then down here when we make the payload. And the payload is literally just going to say, all right, we'll send 24 random bytes followed by the address of the function that we want to execute. And that should be it. Let's try and do that. Let's do Python, and what did I call it? Demo. It's going to run through, and just to show, I've got this set to debug, so you see a lot of output, but this is basically it just doing the first overflow to identify the offset. And you'll see that it came back here and said the offset is at 24, so same as we identified manually. And that means whenever it actually sends the exploit, it's sending 24 bytes followed by this address, and this is the address of the cheat mode function. And it's going to checking cheat code, and then here we go, yeah, checking cheat code, unauthorized access detected. Let's go back and see what that cheat mode function looks like. See here, unauthorized access? Yeah, because we called the function, but it didn't have these parameters set up as they should be. And in fact, I'm going to go and show this even further. Let me do, so here's our jump not 0. This is the address of it, 400728. I'm going to go back to our pwntools script, and I'm going to say in here, let's do break star 0x. Let's do this again, and this time let's do it with GDB. It's going to break at that instruction. So here's our invalid address. Okay. I guess I didn't break at the right place. Let me go back. Oh, let's break at the comparison. Let's do it here. Same again. All right, it pops up and invalid address. Okay. I don't know, do I need to take this out? I know my pwn debug setup messed up a while ago, so I don't really do pwn anymore, so bear with me. Valid address, 0, okay. Oh, it's doing these comparisons one by one, okay. All right, so the function, let's go here then before the first comparison. I thought it was going to put both of those in place and then it was going to compare, but no, it puts the first one in place, it compares it, then it puts the second one in place, then compares it. So that makes sense why it is failing. Let's try one more time. And this time, yeah, okay, so we've hit this breakpoint. You can see here it's moving that value into the RAX. And then next, it's going to do the comparison. So if I now go next, here's the comparison. It's comparing what is in the RAX, which, let's scroll up, RAX is currently equal to these hash symbols. And it's comparing it with what is in the RBP minus 58, which is this. So yeah, they don't equal each other. So whenever it subtracts this from this, it's not going to get 0, which means it's now going to reject it. If I hit next, that's when we're going to run into our error. So yeah, all that to say, basically, we need to go and set up some gadgets. What we can do here is we can do wrapper, and then we can pass in a file. This is our binary, and this gives us all of the gadgets that are in the binary. And we're looking for one to pop the RDI. So I'll do pop RDI, and ooh, we didn't get one. Okay, let me do that again. RDI. Oh, there is one. Yeah, okay. Why didn't it get that? Pop RDI, that looks fine to me. Well, there's the address of one of the instructions we're going to need, because we're going to need to pop one of the parameters in there, the first parameter, and then we're also going to need to do that with the second parameter. So here's one for the second parameter. However, this one also will pop something into the R15, so we just need to make sure there is some junk there as well. I did this kind of an automated way, but I will show how it structures it anyway. You can also make this manually. Let me open up the solve script. And this is doing the same thing as previously, except it's now going to create this ROP object where it'll basically know where all of the gadgets are in the binary. And then it's simply going to call rop.cheatMode. It takes in these parameters and it just builds that into a chain. And it's going to print it out here so you can see what it looks like and how you could have compiled it manually. So let me do Python solve. There you go, we get back our flag, and if you go and have a look at the ROP chain that it created, here it is. So it created an exploit which has pop RDI, and then next in the exploit is the value that's going to pop into the RDI, and then it has the gadget to pop RSI, pop R15. So it's going to pop this into the RSI, and it will pop nothing or just random padding into the R15, and then it will call cheat mode. If you want to see what this looks like manually, you can go and have a look at my GitHub. I did a series where I went through kind of simple pwn challenges like this, and for every one of them, we made a manual exploit and then an automated exploit. So this is really just the same stuff we're going through. But yeah, that's it. Basically, we did a buffer overflow. It's a classic Retro2Win, where we have a win function, in this case, cheat mode, that we can return to once we exploit the buffer overflow. But we first need to make sure that we set up these parameters in place in the RDI and RSI register, otherwise we wouldn't have been able to get the flag. Alright, and that's going to wrap it up for this video. I feel like I'm rambling. This is an easy challenge which shouldn't require a long video. I hope you enjoyed it. If you have any questions or comments, leave them down below. Thanks.